Okay, so today we're going to talk about finding critical numbers, finding absolute and relative extrema. But what we're really going to focus on are what we would call absolute maximums and absolute minimums. Okay? As we go through the week, we will focus more on relative minimums and relative maximums. And going through the week, we will talk about how to find where a curve is increasing and decreasing, where a curve is what we call concave up and concave down, where we have maximums and minimums. So a lot of what we do this week and next week is going to be taking a function and using calculus to figure out what is going on the graph. Okay? Last year in pre-calculus, there were times where we identified minimums and maximums, but we didn't have the math necessarily to actually find the exact value. We kind of like guess where they were. Or in your polynomial chapter, we knew where the zeros were, but we didn't necessarily know where our curve turned. We are going to be able to use calculus to figure all of that out. Okay? So we're going to start off really small. Okay? Let's think about like a relative minimum or maximum. Okay? A relative minimum or maximum is any time our graph changes directions. So maybe we have a hill or a valley. Okay? You have been identifying these maybe even since algebra 2. Okay? On a graph to where you don't do the algebra 4, right? Let's think about how these would correspond to derivatives and what we know about tangent lines and slopes and those kinds of things. So, Owen has an idea.
It would be the x-intercepts.
Okay, so you're right. Our minimums and maximums are the x-intercepts of our derivative. Why is that so?
Because every time it hits a min or an x, it starts going positive or negative, which would mean the derivative graph would be positive or
Okay.
negative.
You said our derivative would have x-intercepts. What's the slope at those 2 points? Okay, so if we have a nice smooth curve, our minimums or maximums would have a derivative of 0, right? Is that the only way our minimums or maximums could look? Change in direction. Tell me a different way they could look. What's the relative maximum there?
There is
Okay. So that wouldn't have one.
Well, what about like a horizontal? Like, couldn't it approach a number?
But is it ever actually getting there?
I mean, technically,
Okay. I like where your head's at. I want you to think of a place where we have a definite change in direction. But it doesn't look smooth like that. Let's think of like an absolute value. Would this vertex of an absolute value be a minimum point?
Yes.
What do we know about the derivative there?
It doesn't exist.
Okay. We say that it's undefined. It doesn't exist. Okay. So we can have a minimum or a maximum occur either when the derivative is 0 or when the derivative is undefined. Okay? Now, it doesn't have to happen every time, but we call these places critical numbers. Okay? And this is important for you to write down. A critical number is a place where our derivative is 0 or not differentiable, undefined. Okay? You don't have to write all of that down. You can paraphrase it if you want to. So a critical number is when we take our derivative and it's 0 or it's not differentiable there, so it's undefined. Okay? Now, what is important to understand is that Extrema only occur at critical numbers, so a relative minimum or a relative maximum only occur at critical numbers. But just because our derivative is 0 does not mean it necessarily is a minimum or maximum, okay? But this is what's going to help us figure out where we potentially have minimums or maximums, okay? Wherever our derivative is 0 or undefined, okay, that is a potential minimum or maximum. Could you give me an example of a graph that has a derivative of 0 somewhere, but it's not actually a minimum or maximum?
Yeah, like, could you like x squared minus 2 or something like that? Is that
Well, that's always going to have one. This right here. X cubed has a derivative of 0 at x equals 0, but it doesn't actually turn there. It just flattens out and then it increases again. A parabola is always going to have a minimum or a maximum at the vertex.
Yeah.
All right. Okay, I want you to look at this graph. And I want you to determine where we have relative minimums, bless you, relative minimums and relative maximums. Talk about it at your pod. You don't even need to draw this or write it down. Talk about where do we have minimums, where do we have maximums. Okay. Pierce, give me a maximum. B is a maximum. Allie, what is the slope at B? Good. Another maximum, Max.
D.
D. What's the slope there?
0.
Good. Another maximum. Is there another one? Okay, the rest, okay, so let's talk about minimums. Rated a minimum.
E.
What's the slope there?
0.
Good. Another minimum, Heidi. What's the slope there? Okay, that slope is undefined. Good. Now, F and A, are they anything? No, they're not anything. Okay. We'll talk about what they are here in a little bit. Okay. Come on. There we go. Okay, so what we're going to talk about today are absolute minimums and absolute maximums. Okay, so if I'm asking you for the minimum, usually I'll say absolute minimum. I'm asking you for the very, very lowest point on the graph. Vice versa. Absolute maximum is the very, very, very highest point on the graph. Now, not all graphs are going to have an absolute maximum and or an absolute minimum, okay? It might not contain either of them, especially if it's a polynomial. Like if you think of any sort of odd degree function, it's going to go on forever in both directions. It's not going to have an absolute maximum or an absolute minimum, okay? A quadratic is going to have one of them, right? A quadratic was going to have either the absolute minimum or an absolute maximum. But you're not guaranteed to have one or the other. Okay, so let's talk about this graph right here. Okay, this is the graph of y equals x squared, and I graphed it from all real numbers. Okay, does this have a maximum? No. But does it have a minimum? Okay, minimum at x equals 0, right? Well, let's take this graph and let's graph it from 0 to 2. Okay, well now what do we have? We have both, right? We have a minimum at x equals 0 and we have a maximum at x equals 2. Okay. What if I say 0 to 2 where 0 is not included? So we have this graph right here. What do we have? We only have a maximum at x equals 2, and there would not be a minimum. Okay. Okay. So the place where we had both was where we made it a closed interval. Okay. That's going to happen every time, and that's the situation that we're going to focus on today. All right? If f is continuous on a closed interval, then on that closed interval, we can identify a maximum and a minimum. Okay. Now, it's important to note that there could be a lot of different things happening on our interval. Okay. The interval that we looked at here, our function was just increasing. So our starting point was our minimum and our ending point was our maximum. Now, a lot of different things could happen in between. Okay, we could have our minimum and maximum occur inside the endpoints. Okay, so the process, let me kind of show you. So this was our graph, right, where we started at the minimum and we stopped at the maximum. Or we could have something like that, where our max occurs here and our min occurs here. Well, that's where our calculus is going to help us, because we know that at the critical points we could have maximums and minimums. So when our derivative is equal to 0, those are potential minimums and maximums. Okay? So in order to figure out on an interval where we have an absolute maximum and an absolute minimum, these are the steps that we need to take. Okay? I think I have, are there 4 of them?
Yes.
Okay. Step number 1, find your critical numbers. We find critical numbers by setting our derivative equal to 0, or figure out where it's undefined. okay? And throughout the entire week, we are going to be working on finding critical numbers, okay? It's not just a Monday thing, it's an all-week thing, all right? Finding where a derivative is undefined will often come when we have some sort of fraction. We can't divide by 0, and if 0 makes our denominator, or if we have a number that makes our denominator 0, that's not okay. All right? Once you have your critical numbers, then you need to evaluate your function at those critical numbers to figure out where you are. Basically, you're finding the coordinates, right? What's the y value at your critical numbers? The reason this is important is because we're looking for absolute. What is the highest? What is the lowest? Our endpoints matter, don't they? Okay, because our endpoint could be higher than our maximum based on the little chunk that we took. So you're also going to need to evaluate the endpoints. What are your endpoints? What are your critical numbers? And you need y values for all of those. Then at that point you can make a decision. Okay? Whichever y value is the smallest, that's your min. Whatever y value is the largest, that's your min. Well, you're not going to solve it.
I went to lunch.
All right, first example. Let's do it. My goal is to do 3 examples, and we have 18 minutes to do so. I think that's a possibility. Okay, what kind of function do we have? What kind of function is this? It's linear, isn't it? Don't make it more complicated. Don't do the quotient rule on this. 2x plus 5 over 3. What is our derivative? Our derivative is just 2/3, right? This is 2/3 x plus 5/3 as a function. So our derivative is 2/3. Okay? All right, when is our derivative equal to 0? It's not a trick question. Can it? Okay, we don't have any critical numbers. That's what that means. Okay, I didn't want you to have something like this in your homework and kind of panic. Okay, it's possible we don't have any critical numbers. Okay, this function is always increasing. All right, so here are our endpoints, 0 and 5. We have no critical numbers to plug in. That's fine. So we can plug in our endpoints, 0 and 5. When we plug in 0, what do we get? When we plug in 5, what do we get?
5.
What do we get? 5.
Or yeah.
I'm seeing what you were in. Sometimes I make mistakes on there and then I never fix them because I'm just okay, so we have an absolute max at the coordinate 5, 5. And we have an absolute minimum at the coordinate 0, 5 thirds. 5 is bigger than 5 thirds. That's how we made that decision. Okay. All right, let's look at one where the algebra is a little bit more exciting. Holding him down.
If I'm this lunch, I guess I'll just have to buy some chocolate.
We need to get you healthy. Okay, so we have an interval. We know we're going to need to plug in -1 and 3, but before we can do any of that, we need to identify critical numbers and figure out if we have potentially minimums and maximums there. All right, so our derivative. Courtney, what is
2 minus times 2/3.
it? Mm-hmm.
Do that now.
X to the
To the 1/3.
Okay, so those 3 cancel, and we have 2 minus x to the -1/3.
Right.
2. There's a 2 there. Okay? Now let's talk about this because we need to figure out where this is 0 and where this is undefined. So technically, we have 2 minus 2 over x to the 1/3. Do you agree? Okay. So if I'm going to have to identify where this is 0 and undefined, it might be helpful to have one big fraction. That way I can figure out where it's 0 and where it's undefined. So if we made this one big fraction, we would have 2x to the 1/3 minus 2 all over x to the 1/3. Okay, how did I do that? We need common denominators in order to subtract. So if we multiply this by x to the 1/3 over x to the 1/3, we would get common denominators in order to be able to put those together. Okay, so where is our derivative equal to 0? If I set this equal to 0, x would be what? Okay. 2x to the 1/3 minus 2 equals 0 gets us to x to the 1/3 equals 1, so x is 1. Okay. How about undefined? Why, Owen? Okay, if our denominator is 0, that means our fraction's undefined. So our derivative is undefined when x equals 0 because that makes our denominator 0, right? It's kind of like the horizontal and vertical tangent lines we talked about. Right? Okay, so we have two critical numbers. We have a critical number of 1 and we have a critical number of 0. We also have an interval from -1 to 3. So we need to find the function values at our endpoints, but then also at the critical numbers. Okay, let's do this. Back up to the function. We want function values. If we plug in -1, 2 times -1 minus 3 times -1 to the 2/3. How about what's -1 to the 2/3? It would be 1. Because the cubed root of -1 is -1, and then the 2 means square, so that would turn to positive, right? So what's our function value? -5. There's a nice one for you. What's the function value at 0? And it is 0? Function value at Brindley.
How did you get -5?
When we plug in -1 to the 2/3, that gives us a +1 because it's the cubed root of -1 squared. So we have -2 minus 3. Okay. What about when we plug in +1? We would get 2 minus 3, right? Okay. Now 3 is not the nicest number to plug in. Okay. In 3, when we plug in 3, it's 6 minus 2 times the cubed root of 3 squared. Okay, there's no way to simplify that. But what's the approximation of it?
2.12.
What?
2 point something.
2 point something? Is it in Trenton with a
-0.240. Oh, I forgot about the series.
yes, that's it. Okay. All right. Can we make our decision now? I'm going to write my answer a little bit different this time. Okay. What's the biggest number you see for a y value? 0. So we have an absolute max of 0 at x equals 0. I'm just writing it a different way for you to kind of see what we're talking about here. What's the smallest number you see? -5. We have an absolute minimum of -5 occurring at x equals -1. Okay? It's the y value that tells us min or max, and it's occurring at whatever the x value is. Okay? Questions? Okay, one more example. And I chose some derivatives that we're not used to having to simplify so that we could go through. Remember when I said just take the derivative and stop. Like, don't worry about the algebra to simplify. Okay? Well, now we have to worry about the algebra to simplify, and so some of these we really need to talk about what that would look like. Okay? So when we take this derivative to figure out our critical numbers, what rule do we have to keep in mind? Overall, we do have a product. X times the square root, right? And you're right, we have a composition with that radical. Okay? Now, do we like to write square root, or we like to think in our head that that is x plus 4 to the 1/2 power? Okay? So when we take our derivative, and you all have your deriver's license, so you know how to do this. Derivative of x, 1. Plus x times the derivative of the radical. So 1/2 x plus 4 to the negative 1/2. And then what's the derivative of the inside? 1. Okay, well, we have to figure out where this is 0 and undefined. And right now, it does not look like a nice equation to do that with. So anytime you have any sort of negative exponent, I would encourage you to write that as a fraction where the exponent becomes positive. So I would encourage you to write this as x plus 4 to the 1/2 plus x over 2 times x plus 4 to the 1/2. So that 2 is in the denominator because it's 1/2. And then the negative 1/2, when we move it across the fraction bar, becomes positive. Okay? It's a lot nicer to figure out where this is 0 and undefined if we actually have one fraction. So in order to get one fraction, what are we going to have to do? We are going to have to make common denominators. So this has a denominator of 2x plus 4 to the 1/2, which means this also should have that denominator. Now this is nice though, right? It works out for us algebraically because what happens when we take x plus 4 to the 1/2 times x plus 4 to the 1/2? X plus 4 to the first power. Questions about that before we simplify it all the way? Okay, so our derivative is 3x plus 8 all over 2 times x plus 4 to the 1/2 power. We have two critical numbers. What's one of them?
-4.
Why is -4 a critical number?
0 in the denominator.
That would make our denominator 0. Boo, that's not okay. Okay. If our denominator is 0, then we would have an undefined derivative. What's our other critical number? -8/3, because that's where our derivative is 0. Okay. Now I think time is almost up. Where did our interval go from? What? -3 to 1. Oh, -4. Is that in our interval?
No.
Then I don't really care about that critical number. I mean, we did the work to find it, and that's going to be beneficial for us down the road. But we don't need to worry about it because it's not in our interval. Okay. So our absolute max is at 1 square root of 5, and our absolute minimum is at -8/3, comma, -3.079. I just did that for you to help us on time here. So there's going to be a majority of them you don't need a calculator for, okay? But if, like, trying to evaluate -8/3 in that square root, like, it's just not great, okay? Okay, so you have a homework assignment. It's not too long. It's not too long. Okay? I need you to be consistent with your homework this week.